let's open it up to the general discussion among the participants.
The question that I wanted to do to Martin at the beginning, but my microphone wasn't working at that moment. So I noticed the difference of standard used when the expanding universe hypothesis is tested and when the static hypothesis is tested. Okay. We have seen that distant galaxies are seen small, and there is no question about that. Of course, that is a blatant contradiction to lambda CDM. But then people say, oh, okay, no problem. There is evolution, there is size evolution, and that's it. And then Martin showed that there is time dilation. So supernova, the light curve of supernova do present a time stretching. So the event is observed to last longer. And this is used to demonstrate that the static model is wrong. But then I say, and why don't we claim that there is evolution of the supernova? So supernova may evolve so to mimic an expanding universe. It would be exactly the same way to reason that we use for the galaxy size. I hope I'm explaining myself.
Yes,
so we
yes,
have used the same standard. If things are allowed to vary and evolve, then we are lost. We cannot prove any model.
I think I agree with you, and this is from the methodological point of view, it's not fair because some things are allowed for the standard model. They can do whatever they want. They can put evolution when they like, but when they try to analyze the works of others, they use other standards. So the methodological is not the same. I totally agree. But nonetheless, and this is connected with something that I wanted to ask you in your work. For sure, you are not taking into account any evolution in your analysis, and well, there are many things to take into account there. You can assume, okay, if we are in a static universe, we can assume there is no evolution. We can explain everything without evolution. This is okay for the evolution of sizes. You can assume that there is no evolution of sizes of galaxies with the same mass. But however, there are some differences between the galaxies at high redshift and the local redshift. The difference is the age. We know because there are measurements, there is a spectroscopy, there are many works about that the galaxies at high redshift are younger than the galaxies in the local universe. And if they are younger...
Okay, so what you are saying is completely correct. But there is one important point to make. We are studying these galaxies in the rest frame UV, and the light in the UV is emitted only by young stars. So, irrespectively of the redshift that we are probing, we are only sensitive to the few young stars that are present on the galaxy. So if you want, the only thing that we are assuming, if you want, is that the star formation rate is sort of constant. And so the galaxy will have approximately always the same amount of young stars.
Well, no, I don't think
it's not correct.
I don't agree with Riccardo, what we're measuring there. What we're looking at is young populations of stars. Yes. We're looking at galaxies that have young population of stars because those are the only galaxies that are going to make it into our selection, because those are the very bright, those are the brightest in the UV. To be bright in the UV, you have to have a young population of stars. So what I make the analogy is we're looking at baby galaxies They're not babies in the sense that they're small, because galaxies don't grow the way people grow. They're babies in the sense that they have a young stellar population. And we're only saying no evolution in their characteristics, because we're saying this is on the assumption that the physical processes in the universe, the basic way they take place, has not changed. But the conditions that they act on has changed. In other words, this is not a steady state hypothesis. The steady state hypothesis that says there was no evolution in the universe is like the homogeneous hypothesis. It's a philosophically derived, not a scientifically derived process. Everywhere we look in the universe, including on our own planet, which is important to us, there is evolution, there is change. For example, if we look at the data accumulated by JWST on the abundance of galaxies going out with redshift from a non-expanding space standpoint, we see that there were fewer galaxies way back when at high redshift. But we see that the number of galaxies was growing rapidly as we move to lower redshift, which is not the case at low redshift. So the analogy is, if today on our planet we go to Africa, we will find the average age of the human beings is much lower than it is in the United States or Japan. But we do not conclude that the African population came into existence 20 years ago, which is their average age. We conclude that they have a higher birth rate. And that's the same with the evolution. You don't conclude that the universe is young when you're looking at galaxies that are young. The birth rate way back when proportionally might have been much greater. That's one point. I do want to comment on this supernova. I may be abusing my chair right, but these observations are based on interpretation of data. And in the case of the supernova, there's a circularity in the interpretation, because you have to get from the supernova data the relationship between the width of the light curves, which is how fast the supernova is fading, and the wavelength at which you were observing it. And in order to derive that relationship, people used the assumption that the expansion was correct. But if you don't use that assumption, if you simply statistically say these are three variables, which is wavelength of light, the width of the curve, how rapidly they decay, and the redshift, then you can say, what is the relationship that minimizes the variance? So I did that. And if you do the correlation correctly as a statistical correlation among three variables, then this is what you get as the correlation between the width of the supernova decay, which is the length of time the supernova takes to decay, and the log of 1 plus z. And what you find is that there's no correlation. There is not any stretching in time. If you assume that there is stretching in time, use that to derive the correlation of wavelength and decay time, then you get this plot. So then you get the correlation of width with log Z, but look what's happened to the scatter. The
Eric,
scatter's gone way up because you're doing the statistics wrong. So that's the answer, is that if you analyze the data correctly, there is no correlation between the decay of the supernova and their redshift.
Eric, I don't know exactly what you are showing there, but the supernova, I understand, they are calibrated with the local supernova. They don't need cosmology. The templates of the light curves are calibrated with the local supernova. So
the templates are calculated using the assumption of cosmological time stretching, and they use a sample that goes far enough into redshift space that it's heavily affected by that assumption. I mean, there are papers that have been published by others that show this, but the analysis that they've done to create those templates is circular from the standpoint of testing whether there is expansion. And if you do a non-circular
may I say something?
Yeah.
Yeah, it is irrespectively of whether there is circularity or not. I mean, the supernova, at least to me, they seem the strongest point in favor of expansion. But still, you can imagine there is evolution. So exactly what is that for galaxy? They say, no, galaxy do evolve in size. So you can say, well, supernova do evolve, and the light curve is different at higher redshift, and that's it. And so you have to explain the evolution in some funny way as you wish, so to retain that the universe is static. You see, Martin, you see the point?
I agree. I agree with you, Ricardo.
Okay.
I agree. Of course, there are some limits in the because we know how much is the evolution of the supernova. Nowadays, there are some studies that they change the magnitude of the supernova. They are not perfect standard candles, we know, but there are some limits. You cannot put the evolution that you like in order to fit your data. There are some constraints.
Anyway, supernova occur when the Chandrasekhar limit is overcome. So maybe the evolution reasoning doesn't make any sense for the supernova, because we have a certain amount of mass that had to explode in order to obtain the supernova name.
How about if the Chandrasekhar mass itself evolves with time?
Well, that leads to a question for you, Rajendra, which is, so do you have an answer to, a tentative answer to the question you asked at the end of your thing? Is there any observational test of the CCC theory? Because if there are no observational tests of it, it's not really a scientific.
The observational tests in cosmology, yes. But people say it is also possible right on Earth. And I have went around various labs, which are for the standard lab, measure Planck's constant, Planck's speed of light, gravitational constant, and all sorts of things. And they say that the methods which are used for that, the equations which are involved in that, when you analyze them, they cancel the variation. So you can't detect it. This is one of the problems. So we, in the cosmological time scale, yes. But then those are, one could say, can you prove that? Can that be explained by another method if we try to detect that kind of thing?
Yeah, well, as I said, that comes back to the methodological question I raised at the beginning of my thing. I mean, I'm just going to ask for a show of hands. Do the panelists, does each panelist agree with the statement that the only test of scientific validity is a comparison of predictions with subsequent observations.
Agreed.
Yeah, I agree, but again,
Does anyone, let me put it this way,
always
does
be-
anyone disagree with that statement among the panelists?
See, I agree, but the situation is not so simple. I mean, if you have a simple theory, then you can make a simple prediction and then compare it with observations. But if you have a sophisticated theory, then you have a lot of steps between your prediction and the observations. So this is something that I have been studying in philosophy of science. That I mean, the Popper dream that you can make a test of a theory by looking at the prevision is not so simple nowadays. If you have something sophisticated, okay, because there are many steps.
Yeah, predictions themselves can be circular in some way sometime, and this is one has to be careful.
I'm not a panelist,
But it seems to me that if,
sorry,
it does seem to me that if a theory cannot be invalidated by observations made after a theory makes predictions, then the theory is not scientific because it can predict anything. I mean, to give a concrete example, I participated online in this open conference that was given by the STSCI Institute that runs JWST. And it was mostly observers presenting their observations and saying, oh, wow, isn't this interesting? Maybe it conflicts with X, Y, and Z. But there was a lonely theoretician who was putting up his simulations about this question of the abundance of galaxies at higher Z. And he put up this slide which showed that there was a gap of a factor of 10,000 between the predictions of his simulation and the JWST observations. There were 10,000 times more galaxies observed at high redshift than he predicted. And he said that this wasn't really a problem because if you changed one variable, which he called stochasticity, which I would randomness, and the line jumped as he changed this variable by a factor of 10,000. So it was a perfect fit to the observations that he now knew were made. So I would say that a simulation that can be easily adjusted to cover a range of 10,000, it doesn't predict anything. And in fact, it isn't a scientifically useful simulation. It's a waste of time. So I think that if we're going to do science that actually is going to involve an increase in our valid understanding of the universe, it's going to have to involve theories that make predictions that can be contradicted or confirmed, not that can be. If you have a theory that can simply be indefinitely modified, you're not validating that theory. And I don't think that theory is scientific.
I think many theories are that make the kind of prediction that is almost impossible to test. Those kind of predictions to me are useless, really, because if your technology within the foreseeable future cannot test it, then you are making prediction which nobody can verify, so you can as well say, yeah, my theory is good.
Right, but as I say, does this qualify as science? I think that it,
Yeah,
I mean,
exactly.
Well,
So
but
it has to be
if
tested.
you
I
can
agree.
make, if you can make prediction, no matter how difficult to verify them is, you are still making prediction, which makes sense. General relativity made prediction that were tested decades later, or even almost a century later than they were made. So,
But some of
or
those
the
predictions,
discovery of neutrinos.
no, but some of those predictions were tested very shortly after they were predicted.
Yes, some
Yeah,
of them.
many,
yes,
yeah,
others
but that
not.
itself is very important, because if you make some predictions and they are tested within a foreseeable time future, then I think it's a good theory. But if you say, this will be, the technology will be developed 200 years later, so you tested that time, that, to me, I think that's not a good theory.
well, I think that the question is not how much time, it's the question of whether an unambiguous test can be made even in theory. In other words, look at the Tolman test. Tolman invented this test in what was it, 37, 36? It was only a matter of a few years after the expansion theory was formulated. And the data to test it really came with HST. So that was 60 years later. But it constitutes a very clear-cut prediction and test. What I'm talking about is if you take a theory and you basically say, my theory has an unlimited number of free variables, and if I can fit the free variables to already existing observations, then my theory is valid. Then, in my view, that is not the scientific method. That is the method of Ptolemy. And that doesn't lead to validity. I mean, I make the analogy that it's the difference between an airline that says, we guarantee that 99.999% you get on this plane, you'll get to the other side of the ocean safely, and an airline that's crashed 16 out of the last 17 flights, but can explain after it's crashed why it crashed. And, you know, I think we should get off of that airline, which is the Big Bang, the Ptolemaic method, and get on the other one, which is about predicting results before they happen.
In my opinion, we have to be...
Riccardo, I'm going to interrupt you because I want to give an opportunity. I guess not everybody among our panelists is still here, I'm sure. But Martin, you must be the one who's staying up the latest. But all right, I want to make sure that everybody gets a chance to speak. But okay, go ahead, Riccardo.
I wasn't speaking, Eric. Martin was speaking. So Martin, please go ahead.
Oh.
No, just to say, since you asked the opinion of everybody, in my opinion, cosmology is not a science like other sciences. Cosmology is something special. It's a mixture of, it has scientific elements, but has also many metaphysical elements and many prejudices. And we cannot test metaphysics. There are some ideas that cannot be tested. Simply, they are prejudices of the people. And this has been always like this in the history of philosophy and science. There are things. Relativity cannot be compared with cosmology. Relativity is a serious theory. It's a completely mathematical theory that can be demonstrated. But cosmology is a model in which there are some principles that cannot be demonstrated. Simply, they are put there because we believe in that. We cannot know how are the laws of physics at the beginning of the universe. We assume that the laws of physics are the same here that at the beginning of the universe, but we cannot test that. Or if we can test it, there are many ways to do it. So it's totally impossible to verify all the models. In my opinion, we have to forget about the idea that the next observation of the James Webb is going to consolidate forever that the universe is expanding or not expanding. No, there is a social element that we are not going to remove at all. It doesn't matter how many data, how many telescopes we are going to build. There will be always some group of leader cosmologists that will try to save the theory in the Ptolemaic way. It's not scientific, of course, it's not scientific, but cosmology is not totally scientific. Has few scientific elements, but it's not totally scientific.
I agree.
Agree.
I also agree.
I disagree. I think that the non-scientific elements are right, non-scientific. They are imposed on cosmology for ideological and other social reasons. But there is a science of cosmology, which is simply the science of astrophysics on the largest scales. And I think that, you know, we have to look historically. The situation of cosmology did not always exist. It came into existence in a process almost exactly a century ago, in which non-scientific principles were introduced into science and became eventually dominant within this field of science. And I think that there has to be a battle to expel those non-scientific principles. That's what happened, 400 years ago, in which, the Ptolemaic method was dominant for all of physical science, the Aristotelian. And it took quite a battle, but eventually that method was overthrown and it was discredited for a period of centuries until it was reintroduced in the early 20th century. So I think that although it's taken a lot longer than most of us would have expected, I think that it is a battle that can be won, that must be won, because at the moment, the unscientific version of cosmology is really acting to discredit science in the eyes of the general population. I think the fact that the media has highlighted cosmology as sort of the highest point of physical science, and the fact that these very unscientific concepts are being touted as the essence of science discredits the entire scientific enterprise. So I think that it's an important battle. It's not an easy battle, but I think it's a battle that absolutely has to be won.